Good morning, students. Today we see about the 11th standard physics 7th unit, the continuation of this lesson. Okay. Today we see about the angle of contact. Angle of contact. What is mean by angle of contact? Anybody knows the answer for this? Okay, I will say the answer. First, here I take one beaker. Okay, here I take one beaker. The beaker is filled with some water. Okay, the beaker is filled with some water. Now I placed one plate. Now I placed one plate here. Okay, that angle, that make the angle between that beaker and the glass plate, that is called as the angle of contact. Okay, it make the angle theta. Okay, are you understand? So this is called as the angle of contact. So here, when the free surface of a liquid comes in contact with a solid, when the surface of the liquid becomes curved at the point of contact. Already I said, it may take one beaker, that beaker is filled with water, then placed one plate on that beaker. That angle, that make the angle between the beaker and the plate, that is called as the angle of contact. That curved point, that is called as the point of contact. Okay. Here, whenever the liquid surface becomes a curve, then the angle between the two medium, that is the solid and another one is liquid, that beaker is solid and the inside some liquids are there. So the two medium comes in the picture. For example, when a glass plate is dipped in water with sides vertical, see the figure, take page number 76 and see the figure 7.26. Okay, here we can observe that the water is drawn up to the plate. In the same manner, instead of water, the glass plate is dipped in mercury. Suppose now we take one beaker. The beaker is filled with full of mercury. Okay, instead of water, it is filled with mercury. The surface is curved, but now the curve is depressed. Okay, it make the curved surface, but the curve is depressed. Here, the angle between the tangent to the liquid surface at the point of contact and the solid surface inside the liquid, this is known as the angle of contact between the solid and liquid. Already I said it denoted as, the angle is denoted by theta. Here its value is different at interfaces of different pairs of solids and liquid. In fact, it is the factor which decides whether the liquid will spread on the surface of a chosen solid or it will form the droplet on it. Let us consider here three interfaces they take. One is the liquid air, and another one is the solid air, and another one is solid liquid. So here we consider the three interfaces. What are they? Liquid air, solid air and solid liquid. Okay, three interfaces with the reference points. All contain the reference point at the point of contact is taken as O. Okay, here, and the interfacial surface tension forces, that is that TSA means surface tension for the solid air. Okay, then TSL, surface tension for the solid liquid, and TLA, surface tension for the liquid air. Okay, then see the figure 7.26. Okay, see the figure 7.26 here, the angle of contact of a liquid. Okay, here on take one beaker and inside that liquid is there, so it make the angle theta. Okay, the center point, that is the point of contact, is denoted as O. Here, since the liquid is stable under equilibrium condition, okay, here the liquid is under the equilibrium condition, the surface tension forces between the three interfaces. Already we take three interfaces. What are they? Solid air, liquid air and solid liquid. So three interfaces they take. Here the interfaces must be also in, liquid is in stable equilibrium, means that interface is also in the equilibrium state. So see the equation. So see the equation here, TSA, which is equal to TLA cos theta plus TSL gives the equation is TSA, that is the surface tension of solid air, which is equal to the tension of liquid air cos theta. Here it make the angle for solid and the liquid. So here we take solid air and liquid air and it make the angle cos theta plus what is that? Surface liquid. Okay, here we want only consider the cos theta because we want to find the value for theta. So cos theta, which is equal to, I take this TSL to this side. Okay, so here it is positive, means when it come to the after equal to sign it changes into negative. So here TSA minus TSL upon TLA. Okay, this is taken as equation number 1. So next step, from the above equation, now we find the cos theta value, that is the cos theta which is equal to TSA minus TSL upon TLA. Okay, next here 3 different possibilities are there. Okay, suppose first case, if TSA, that is the solid air greater than solid liquid, means that solid air minus solid liquid, that value is also greater than 0. Here in that case means the angle of contact that take place between the water and plastic. Okay, என்னது இங்கே வந்து வாட்டருக்கும் பிளாஸ்டிக் திங்ஸ்க்கும் இடையில இருக்கக்கூடிய இன்டர்ஃபேஸ். ஓகே, ஹியர் இட் மேக் த ஆங்கிள் ஆஃப் கான்டாக்ட் theta is an acute angle. What is mean by acute angle? The theta value will be less than 90 degrees. So that is called as the acute angle, and the cos theta value is also positive. Okay, the cos theta value is also positive. So this is the first case. In this case, here the surface air is greater than surface liquid, and the surface air greater than surface liquid means that value will be minus TSA minus TSL, that is that 0, that value will be greater than 0. So here the angle of contact that take place between the water and plastic interface, so that here it make the angle of contact theta, that theta value will be acute angle. Acute angle means the theta value will be less than 90 degree. Here the cos theta value will be positive. Okay, you understand? So this is the first case. In second case, here the TSA, that is the tension of solid air is less than solid liquid, means here also minus TSA minus TSL, but here the value is less than 0. In first case the value is greater than 0, in second case the value is less than 0. Okay, in first case what are the interfaces? Water and plastic. Here the water and leaf interfaces, so that in that case, in first case the angle of contact is acute angle, here the angle of contact is obtuse angle. Obtuse angle means that theta value is less than 180 degree and greater than 90 degree. You understand? So that here the theta value is greater than 90 degree means the cos theta value will be negative. In first case the cos theta value will be, in this case the cos theta value will be negative. Okay, then last case, that is the third case, here the TSA greater than TLA, that is the tension of solid air is greater than liquid air, but here the TLA is plus TSL. Okay, TLA plus TSL, that means there will be no equilibrium. The liquid is not in equilibrium condition and the liquid will spread over the solid. Okay, the liquid will spread over the solid, so there is no angle of contact take place in that type of liquid, in that type of interfaces. So here in angle of contact, here consider the 3 cases. First case, the TSA minus TSL, that is the value will be greater than 0, so that the interface is water and plastic interface. It make the angle theta, that theta value is an acute angle. Acute angle means it is less than 90 degree. So the theta cos theta value will be positive. In second case, yes, the TSA minus TSL is greater than 0, less than 0. Here the interface is water leaf interface. The angle of contact is obtuse angle. Obtuse angle means less than 180 degree and greater than 90 degree. Here the value will be greater than 90 degree, so that the cos theta value will be negative. In third case, the liquid is not in first two cases the liquid is in equilibrium condition, so that the angle of contact will take place that. But in third case, here the angle of contact, here the equilibrium, there is no equilibrium in the liquid, so there is no angle of contact. The liquid will spread over the solid. Okay, so that here therefore the concept of angle of contact between the solid liquid interface leads to some practical applications in real life also. For example, soap and detergent. This is the solid liquid interface. Soap and detergents, these are the wetting agents. Okay, soap and detergents are the wetting agents when they are added to an aqua solution. Okay, soap detergent powder when we mix with water, aqua solution means water, they will try to minimize the angle of contact and in turn penetrate. What is meant by penetrate? Okay, so and in turn penetrate well in the cloth and remove the dirt. Okay, so this is the practical applications of the angle of contact between the between the solid liquid interface. Okay, on the other hand, waterproofing paints are coated on the outer side of the building so that it will enhance the angle of contact between the water and the painted surface during the rainfall. Okay, வாட்டர் கோட்டிங் பெயிண்ட்டை வந்து அவுட் சைடில் நம்ம இது பண்ணும்போது அது வந்து என்ன பண்ணாது, ரெயின்ஃபால் வந்து அதில் ஆங்கிள் ஆஃப் கான்டாக்டை டச் பண்ணாது. அந்த மலைத்துளி வந்து அந்த இதில் வந்து பட்டாலும் இட் cannot மேக் எனி ஆங்கிள் ஆஃப் கான்டாக்ட். ஓகே, ஸோ தட் ஒன்லி இட் வில் பி enhance the angle of contact. Okay, have you all understand? So two practical applications are there. One is soap and detergent and another one is waterproofing paints. Okay, next we see about the excess of pressure inside a liquid drop, a soap bubble and an air bubble. Okay, first, as it is discussed earlier, the free surface of a liquid become curved when it has contact with a solid, depending upon the nature of liquid air or liquid gas interface. Here the magnitude of interfacial surface tension varies. In other words, as a consequence of surface tension, the above such interfaces have energy, and for a given volume the surface will have minimum energy with the lost area. Due to this reason, the liquid drop becomes spherical for smaller radius. Okay, why the liquid drop will be spherical in shape? Because due to this, here depending upon the nature of liquid air or liquid gas interface, the magnitude of interfacial surface tension will be varies. Okay, so in other words, as a consequence of surface tension, the above such interfaces, what are the interfaces? Liquid air and liquid gas interfaces. Here the energy, it has some energy for a given volume, so that here the surface will have minimum energy with the least area. Okay, when the area will be least means that surface tension will be, that surface area will have the minimum energy. For this reason only the liquid drop becomes spherical in shape. Okay, then next, when the free surface of the liquid is curved, there is a difference in pressure between the inner and outer the side of surface. Okay, but the free surface of the liquid is curved in shape. Why? Because there is a difference in pressure between the liquid and outer side of the surface, so that it is a curved in structure. Okay, then next see the figure 7.27, excess of pressure across a liquid surface. Okay, then see that curved structure, excess pressure, that is outside, and inside also it has some pressure. Okay, next, when the liquid surface is plane, the force due to surface tension, that is the T, act tangentially to the liquid surface in opposite direction. Hence, the resultant force on the molecule is 0. Therefore, in the case of plain liquid surface, the pressure on the liquid is equal to the pressure on the vapor side. See the figure 7.27, that is the first diagram, that is the straight diagram. Here when the liquid surface is plain, okay, there is no curve, there is no spherical. Here the liquid surface is plain. Here the force due to the surface tension act tangentially to the liquid surface in opposite direction, so that only here one arrow is there, here one arrow is there, and another one arrow is there. Okay, here one arrow and here one arrow is there. Okay, because it make tangentially, so that it two opposite directions are there. Hence the resultant forces on the molecule is 0. The resultant forces of the molecule is 0 because both are in opposite direction. So there is no resultant force. Therefore, in this case, a plain liquid surface, the pressure on the liquid side is equal to the pressure on the vapor side. Okay, then see the next case, that is the second diagram. See the second diagram. Here when the liquid surface is curved, every molecule on the liquid surface experiences the force Ft, that is the force, surface tension of the force, then surface tension of the force due to the surface tension along the tangent to the surface, resolving these forces into rectangular component. Okay, what component is there? Rectangular component. We find the horizontal component cancel out each other while the vertical component get added up. Okay, here the horizontal component will be cancelled, so the vertical component only added. Therefore, the resultant force normal to the surface act on the curved surface of the liquid. Similarly, for a convex surface, the resultant force is directed inward toward the center of curvature, whereas the resultant force is directed outward from the center of curvature. For a concave surface, thus the curved liquid surface in equilibrium, the pressure on its concave side is greater than the pressure on its convex side. Okay, when compared to concave and convex, here see the second figure. Here two structures are there, concave and convex. Here the curved liquid surface in equilibrium. Okay, here the liquid surface in equilibrium, the pressure on its concave side when compared to convex side, the pressure on the concave side is greater when compared to the convex side. Okay, the next, excess of pressure inside a bubble and a liquid drop. Excess of pressure inside a bubble and a liquid drop. Here the small bubbles and the liquid drops are spherical because of the forces of surface tension. Why the small bubbles and the liquid drops are spherical in shape? Because of the forces of surface tension. Okay, the surface tension involves some forces, so that only the bubbles and liquid drops are spherical in shape. Okay, the fact that a bubble or a liquid drop does not collapse due to the combined effect. The fact the bubbles or a liquid drop does not collapse due to the combined effect indicate that the pressure inside a bubble or a drop is greater than the outside it. Okay, so see the first one, excess of pressure inside air bubble in a liquid. Excess of pressure inside the air bubble in a liquid. So that here consider an air bubble of radius r. Okay, here consider this. See the figure 7.28. This is the air bubble. It consists of the radius r. Then have some surface tension that is taken as the T. Okay, that arrow mark that is taken as the surface tension, that is called as the T. Okay, the surface tensions are called as the T. Then let P1 and P2 be the pressure outside and inside the air bubble respectively. Okay, here two pressures are there. One is P1 and P2. P1 is the outside pressure and P2 is the inside pressure. Now the excess pressure inside the air bubble is del P, which is equal to P1 minus P2. Okay, excess pressure, so that is taken as del P. Excess pressure is which is equal to the difference in inside pressure and the outside pressure. So del P, which is equal to P1 minus P2. Okay, consider one air bubble that have the radius or then it have the surface tension T, and it consists of two pressure, that is the outside pressure and inside pressure. So the excess pressure is denoted as del P, which is equal to P1 minus P2. Then in order to find the excess pressure inside the air bubble, let us consider the forces acting on the air bubble for the hemispherical portion of the bubble. Now we take the hemispherical portion of the bubble. Here, considering the forces acting on it, we get first the force due to the surface tension. First, the force due to the surface tension acting towards the right around the rim of the length, that is the 2 pi r. Here spherical surface means that is taken as 2 pi r is Ft, that is which is equal to 2 pi rt. T is the tension of that force. Okay, here first one, the force due to surface tension acting towards the right side. See the figure. Okay, wait. Now the force is acting on the right side of the rim. So here that length is taken as 2 pi r is F 2 pi r. So the surface tension force Ft. Ft means surface tension force, which is equal to 2 pi r T. You all understand? Then second point, the force due to outside pressure. Now we taken the force due to the outside pressure. Outside pressure nala irukkoodiya force நம்ம இப்போ consider பண்ணிக்கோ. So the force due to the outside pressure P1 is to right acting across a cross sectional area. Okay, first one acting the right side, then second one acting the cross sectional area of pi r squared. Okay, here the area is pi r squared. So Fp1, first one is force due to tension, the second one force due to outside pressure. So here consider Fp1, which is equal to P1 pi r squared. Have you all understand? P1 pi r squared. Okay, then the third case here, the force due to pressure. Now inside pressure. Okay, so here P2 is considered inside the bubble acting the left. Okay, so here Fp2 means force due to the inside pressure. So Fp2, which is equal to the similar to the second one. Okay, P2 instead of P1, here we put pi r squared. Okay, have you all understand? So three points are there. First one is three forces are there. First one is the force due to tension. Okay, for that Ft, which is equal to 2 pi rt. Then second one, force due to outside pressure P1. Okay, so Fp1, which is equal to P1 pi r squared. Then third one, force due to inside pressure P2. So that Fp2, which is equal to P2 pi r squared. Okay, as the air bubble is in equilibrium. Now the air bubble is in equilibrium condition under the action of three forces. What are the three forces? Pressure, force due to outside pressure, force due to inside pressure, and force due to tension. So three forces are there. Okay, so three forces are there. We have to add these three. Okay, so first we consider the force due to inside pressure. Force due to inside pressure means Fp2, which is equal to force due to tension plus force due to in outside pressure. Okay, have you all understand? First we consider the force due to inside pressure, that is Fp2, which is equal to force due to tension Ft plus Fp1. Fp1 means force due to the outside pressure. Okay, then what is the value for force due to inside pressure Fp2? P2 pi r squared. Okay, so instead of this Fp2, we have to apply P2 pi r squared. Then what is the value for Ft, that is force due to tension? 2 pi r t. Okay, then what is the value for force due to outside pressure Fp1? P1 pi r squared. Okay, from this case, now I take this P1. Okay, now I arrange this P P are in one side. Okay, P side full one side kondu vandirken. So I can take P2 pi r squared, then minus, here I take this P1 pi r square to this side. So here positive is there. When come to this side means it changes into negative. So minus P1 pi r squared. Okay, we all understand? Okay, from this I take what are the common terms are here. Here also pi r square is there. Here also pi r square is there. Okay, so I take this pi r squared common. Okay, so I take this pi r squared common. Then what is the remaining thing? P2 minus P1. Okay, P2 minus P1. Have you all understand? So this is this step. Okay. Here we have to apply the value for these three forces. Then I take this P1 to this side. So here it changes this plus to minus. So then next step I take this pi r square common. So what is the remaining thing? P2 minus P1 pi r square, which is equal to 2 pi RT. Okay. So excess pressure is del P, which is equal to, this is the excess pressure, P2 minus P1. Okay, P2 minus P1, which is equal to, in next step, what is we already find that what is the value for what is the excess pressure? Del P, which is equal to P2 minus P1, isn't it? This is the excess pressure. Okay, here P2 minus P1 is there. Where? Here P2 minus P1, which is equal to, P2 minus P1 pi r squared, which is equal to 2 pi RT. Okay, we want only this P2 minus P1 value. So I take this, I keep this P2 minus P1 here. Then P2 minus P1, which is equal to 2 pi RT upon, I take this here, it is in multiplication. When come to this side means it comes in the denominator term, that is the division. So upon pi r squared. Okay, so here this pi will be cancelled, and here one r is there, here one r is there. So what is the remaining thing? P2 minus P1, which is equal to 2 pi already cancelled, this r will be cancelled, then 2t upon r. Okay, 2t upon r. So this is here del P, which is equal to P2 minus P1, which is equal to 2t upon r. Have you all understand? So this is the excess pressure. Excess pressure is denoted as del P. That means P2 minus P1. That value will be 2t upon r. The del P, which is equal to P2 minus P1, which is equal to 2t upon r. This is the excess pressure. Okay, next we see the excess pressure inside the soap bubble. Okay, in previous topic we see the excess pressure inside the air bubble in a liquid. In this topic we see the excess pressure inside a soap bubble. So here consider a soap bubble of radius, the same one. Here also consider, see the figure 7.28. Okay, consider the soap bubble of radius r and the surface tension. Here also it has some surface tension that is taken as T. A soap bubble has two liquid surfaces. Okay, here it consists of two liquid surfaces in contact with air one side, the bubble one side in contact with air, one side one inside the bubble and the other outside the bubble. Okay, so two surfaces are there, two liquid surfaces are there, one inside the bubble and the another one is outside the bubble. Therefore, the force on the soap bubble due to the surface tension is, what is the force on the bubble due to the surface tension is 2 into 2 pi RT. Why here we put 2 into 2 pi RT? Here two liquid surfaces are there, one inside the bubble and one outside the bubble, so that the force due to surface tension is 2 pi r t. Here two surfaces are there, so that 2 into 2 pi r t. Okay, so the various forces acting on the soap bubble are, here also three forces are there. First one is the force due to tension, then force due to outside pressure, then force due to inside pressure, the same like the air bubble. Okay, so first we consider the force due to surface tension. What is that? That is denoted as Ft. Ft means force due to surface tension. Already I said here two surfaces are there, so 2 into 2 pi r t, 2 2s are 4, so 4 pi r t, the value for force due to surface tension, which is equal to 4 pi r t. Then second one, next force due to outside pressure, that is Fp1. Fp1 means force due to outside pressure, and Fp2 means force due to inside pressure. Okay, first we see the force due to outside pressure, that is Fp1, which is equal to P1 pi r square, the same like that of the air bubble. Okay, so the next one, force due to inside pressure, that is denoted as Fp2, which is equal to P2 pi r squared. Now the bubbles are in equilibrium, so we have to add force due to inside pressure that is Fp2, which is equal to force due to tension plus force due to tension plus force due to outside pressure Fp1. So what is the value for Fp2? P2 pi r squared. So we have to apply this value for Fp2, then which is equal to, then what is the value for Ft? 4 pi r t. Then what is the value for Fp1? P1 pi r squared. Okay, now I take this P2. Okay, now I take this P1 pi r2 to this side, so it changes into, here already P2 pi r square, then I take this to this side, means it changes into negative, so minus P1 pi r squared. Okay, say here what is the common term? Pi r square is common term, so I take pi r squared common, then what is the remaining term? P2 minus P1, which is equal to 4 pi r t. Okay, so this is the excess pressure. What is the excess pressure? Del P. Excess pressure is denoted as del P, which is equal to P2 minus P1. The excess pressure del P, which is equal to P2 minus P1. So that here we want only the P2 minus P1 value, so I take P2 minus P1, which is equal to 4 pi RT upon pi r squared. Okay, here also pi cancel and 1 RR will be cancelled. Then finally we get the value 4T upon R. 4T upon R. This is the excess pressure del P, which is equal to P2 minus P1, which is equal to 4T upon R. Have you all understand? So this is the excess pressure inside the soap bubble. Then what is the value for excess pressure inside the air bubble? 2T upon R. Then what is the value for excess pressure inside the soap bubble? 4T upon R. Okay, next we see the excess pressure inside the liquid drop. Okay, next we see the excess pressure inside the liquid drop. Here also see the figure 7.28. Consider the liquid drop. It having the radius R, and this it also has some surface tension, so that only it is in spherical in shape. Okay, so that surface tension is taken as capital T. Okay, here also the various forces acting on the liquid drop. First, the surface tension, force due to surface tension, then next force due to outside pressure Fp1, then third one force due to inside pressure Fp2. Okay, first we see the force due to surface tension, that is taken as Ft, which is equal to 2 pi r t. Okay, here only one surface only is there, so that only 2 pi r t, but in soap bubble two surfaces are there, so that they take 2 into 2 pi r t, so the value will be 4 pi r t. Okay, the next force due to outside pressure is denoted as Fp1, so Fp1, which is equal to the same like that of the air bubble and the soap bubble, Fp P1 which is equal to P1 by R squared. Okay, then third one, force due to inside pressure, that is Fp2 which is equal to P2 by R squared. Okay, now the drop is in the equilibrium. Equilibrium means the force due to inside pressure which is equal to sum of force due to surface tension and the force due to outside pressure. That means Fp2 which is equal to Ft plus Fp1. Then we have to apply the values for Fp2, then Ft, then Fp1. This is similar to that of the air bubble. Okay, the air bubble value and the liquid drop value will be same. Okay, what is the excess pressure for air bubble? P2 minus P1, that is the del P which is equal to P2 minus P1 which is equal to 2T upon R. Here also the same value will be there. Okay, so today we see about the, today what we see about the angle of contact. Okay, today we see about the angle of contact. What is the angle of contact? Angle of contact means, say what is the angle of contact? Angle between the tangent to the liquid surface at the point of contact and the solid surface inside the liquid is known as the angle of contact. Okay, between the solid and the liquid. Here this angle of contact is denoted by theta. Okay, here the three cases are there, three interfaces are there. What is that? Liquid air, solid air and solid liquid. So three interfaces are there. Here the solid air is denoted as TSA and the solid liquid is denoted as TSL and the liquid air is denoted as TLA. Okay, so here the what is the formula for is here that liquid is in stable equilibrium condition, so the interfaces are also equilibrium. That means TSA which is equal to TLA cos theta plus TSL. Okay, we have to find only the cos theta value, so cos theta is equal to TSA minus TSL upon TLA. Okay, from the above equation here three possibilities are there. The first possibility is if the solid air is greater than liquid air, means that solid air minus solid liquid, that value will be greater than 0. Here the interface is water and plastic interface. Here the angle of contact is acute angle. Acute angle means the theta value will be less than 90 degrees, so the cos theta value will be positive. Okay, then the second possibility is here if the solid air is less than liquid, solid liquid means that value will be less than 0. Here the interface is water leaf interface. Here the angle of contact is obtuse angle. Obtuse angle means the value will be greater than, theta value will be greater than 90 degree but less than 180 degree, so that here the cos theta value will be negative. Okay, in third case here there is no equilibrium, the liquid is not in equilibrium, so it cannot make any angle of contact. So three cases or three possibilities are there. Next we see the excess of pressure inside a liquid drop, soap bubble and air bubble. First we see the air bubble. Yes, first we see the excess of pressure inside air bubble in liquid, then we see the excess of pressure inside a soap bubble, then finally we saw the excess of pressure inside the liquid drop. What is meant by excess pressure? That is denoted as del P which is equal to P2 minus P1. Okay, then what is the value for excess pressure inside the soap bubble? That is del P which is equal to 4T upon R, but the liquid drop, that is the excess pressure inside the liquid drop and the excess pressure inside the air bubble value will be same, that is 2T upon R. Okay student, have you all understand? So okay, don't waste the time. Today I give some homework for you. Study the take the sixth lesson. Take page number 54. Take page number 19.